Today, we'll be discussing the retention basin, a crucial component in managing stormwater runoff. A retention basin is one of two commonly used best management practices, or BMPs, specifically designed for the quality control of runoff. While often called a retention basin, it's sometimes referred to as a dry pond. This latter name highlights a key characteristic. It remains dry for most of the year, only holding water for short periods immediately following a significant runoff event. Historically, because retention basins were among the first BMPs widely adopted, many regulations have traditionally viewed them as regional solutions, serving very large catchment areas. However, with the emergence of green stormwater infrastructure, or GSI, and the growing emphasis on using BMPs directly on-site, retention basins are now also integrated within broader watershed management plans. In these cases, a watershed might be divided into smaller catchments, with each catchment potentially incorporating its own retention basin. It's also worth noting that many other modern BMPs function using similar removal mechanisms to a retention basin. These include notable examples like permeable pavement, various types of retention rain gardens, swales, exfiltration systems, and retention tree wells. This module will focus on how to effectively use retention-based best management practices, or BMPs, for pollutant removal. To begin, we'll define what constitutes a retention BMP, specifically examining retention basins and how their average annual mass removal effectiveness is determined. Given the complexity of these calculations and the need for timely project completion, we'll then introduce you to the BMPFast software. This powerful tool helps estimate the annual mass removal of total nitrogen and total phosphorus. We'll provide a comprehensive demonstration of how to navigate BMPFast, focusing on its worksheets for retention basin analysis. You'll also discover how to leverage the plot and tools options within the software to explore various solutions for enhancing mass removal. To bring everything together, we'll work through a practical example problem, illustrating the value of retention and the effective use of this software. The Retention Best Management Practice, or BMP, is fundamentally a system designed to prevent the discharge of a specific volume of stormwater runoff directly into surface waters. Instead, it stores this water within the immediate catchment area. The goal is to hold the runoff rather than release it. These systems can take many forms. We often see examples like excavated or natural depression storage areas, which are essentially basins designed to collect water. However, the concept extends to other practices such as permeable pavement, which allows water to seep through its surface, rain gardens, exfiltration trenches, and vegetated swales. All these methods perform the same essential function of retaining stormwater. The volume of water collected and held within these retention areas is referred to as the treatment volume. While this volume is critical, it's important to understand that it's rarely large enough to contain all the runoff from every single storm event. Therefore, a key aspect of designing and evaluating retention BMPs is calculating the percentage of the annual runoff that can be effectively retained. This retained volume is also known as the capture volume. Understanding and accurately calculating the storage volume is essential for determining just how much of the annual runoff a basin can prevent from reaching surface waters. When we talk about the size of a retention best management practice, a common term we use is the treatment depth, or TD. This is typically expressed in inches over the catchment area and represents the depth of water that the BMP is designed to treat from that area. The fundamental relationship is that treatment depth equals the treatment volume divided by the catchment area. So, TD equals TV, area. Conversely, if you know the area and the desired treatment depth, you can calculate the necessary treatment volume by multiplying area by TD. To get the treatment depth in the common unit of inches, you'll take the treatment volume in acre-feet, multiply it by 12 inches per foot to convert it from feet to inches, and then divide by the catchment area in acres. So, the formula becomes TD equals TV, acre-feet, by 12 inches foot, area acres. In many stormwater plans, the retention volume is initially provided, and from that the treatment depth can be easily calculated. This makes it straightforward to relate the annual removal capture or mass removal efficiency to various land uses, considering their pervious area cover, soil types, and directly connected impervious areas. Let's look at an example. If we have a catchment area of 12 acres, with a directly connected impervious area, or DCIA, of 27%, and a curve number for the non-DCIA of 64, and we need to achieve 64.5% annual pollutant removal, which we would determine from a previous analysis, we might find that this requires a treatment depth of 0.33 inches. Using that TD, we can calculate the necessary treatment volume. TV equals 12 acres multiplied by 0.33 inches, then divided by 12 inches per foot to convert back to feet. This gives us a treatment volume of 0.33 acre-feet, which is equivalent to 14,375 cubic feet. Conversely, if we were given the treatment volume first, say, 14,375 cubic feet or 0.33 acre-feet, we could calculate the treatment depth. We'd take 0.33 acre-feet, multiply by 12 inches per foot, and then divide by the 12-acre catchment area, which again gives us a treatment depth of 0.33 inches. Retention effectiveness is fundamentally a function of how much runoff volume a system can capture over time. When we consider fast recovery retention systems, such as exfiltration in limestone or those utilizing pump recovery, the annual effectiveness significantly increases compared to systems with slower recovery times, like those found in less permeable A and B soils. For typical runoff conditions and recovery times up to 72 hours, you would apply the removal efficiency tables found in the new rule, specifically Applicant's Handbook Volume 1, Appendix O. These tables were developed with the understanding that the treatment volume would be fully infiltrated or utilized within the retention device within 72 hours following a storm event. However, for systems exhibiting very fast recovery, such as retention basins that infiltrate their treatment volume in no more than 3 hours, common in limestone areas or with specific media, the capture efficiency must be greater. For these fast recovery scenarios, you'll adjust the base efficiency from the tables using the rainfall graph shown, which allows for an increase in effectiveness of up to 10%. The concept of calculating this capture, knowing the cumulative distribution of rainfall volume over time, has been a cornerstone of stormwater management regulations in Florida since the very first publications. Percent capture curves for recovery times of no more than 3 hours were published by Wanyalista in 1978, and for recovery times of no more than 72 hours by Harper in 2007. These published curves and tables compare the annual capture or effectiveness of runoff water as a function of the system's storage volume and treatment depth, assuming an initial abstraction of 0.1 inch. It's worth noting the practical challenge of interpolating these values for conditions other than standard curve number and DCIA increments. The removal tables from Harper are incorporated into the latest Applicant's Handbook, Volume 1. Here, we're looking at the efficiency of a stormwater treatment system, specifically related to the site's characteristics, the rainfall patterns, and the treatment depth, or TD. The treatment depth is simply the treated volume divided by the area of the catchment. This efficiency is measured as a capture percentage, which represents the fraction of the annual runoff volume that is effectively treated. These capture percentages are derived from extensive long-term simulations of a catchment area at a specific rainfall site. For each unique treatment depth and site condition, over 280 simulations were run to generate robust data. Harper, in his 2007 work, developed comprehensive tables based on these simulations, providing capture percentages for various treatment depths, such as 0.25, 0.50, 0.75 inches, and up to 4.0 inches, typically assuming a 72-hour recovery time for the treatment volume. While the overall methodology and some of these tables are included in the Applicant's Handbook, obtaining precise values for every possible scenario presents a challenge. Specifically, interpolation becomes quite difficult if your site's curve number, or CN, or the directly connected impervious area DCIA don't fall neatly into increments of 5, or if your desired treatment depth is not one of the values explicitly listed in Harper's published tables. This is where a tool like BMPFast becomes incredibly useful. Its Tools menu includes a feature that calculates the capture efficiency for a specific rain region and the defined catchment conditions, considering both the curve number for the non-directly connected area and the percentage of directly connected impervious area. BMPFast handles all the necessary interpolations automatically. For example, if you have a retention depth of 0.33 inches, a curve number of 64, and a DCIA of 27%, values that would not be found directly in the published works, BMPFast can accurately calculate the efficiency. This automation minimizes the potential for errors that can arise from manual interpolation and translation, making the process both accurate and fast. When our initial treatment volume doesn't produce the desired removal efficiency, we need a way to explore how adjustments might improve performance. This is where the plot of effectiveness feature comes in handy. It allows us to investigate marginal changes in effectiveness as a function of the retention treatment depth. Specifically, the plot button in BMPFast can generate a graph showing how varying the treatment depth impacts the removal percentage. This helps us answer questions like, if we need additional removal, do we have sufficient area and storage volume to accommodate a higher treatment depth? And if so, what would that optimal treatment depth be? Remember, the retention depth is directly calculated from the retention volume and the catchment area. So, to increase efficiency, you could either increase the retention volume, or you could decrease the effective catchment area by removing some on-site contributing areas. The plot helps visualize the trade-offs. Additionally, the BMPFast program also provides a Get Depth button, where you can input a desired percentage removal, and it will directly tell you the required treatment depth. We've discussed how recovery time is crucial for stormwater management practices. Field measurements, particularly in areas with highly percolating soils and rock formations like limestone, often reveal that actual recovery times are significantly less than the standard 72 hours. So, what happens when that recovery time is much shorter, for instance, 36 hours? Harper conducted extensive simulations across various meteorological regions to answer this. These simulations indicate that for a 36-hour recovery time, the overall effectiveness, or pollutant removal, can increase by an average of up to 3.5% compared to a 72-hour recovery. This increase approaches zero as the treatment depth reaches about 4.0 inches. For practical application, an average value is used for each rain zone, acknowledging the small variations and the assumed 1% accuracy of these simulations. To integrate this into our calculations, a best-fit polynomial curve has been developed. This curve provides a mathematical relationship to quantify the increased effectiveness when moving from a 72-hour recovery time to a 36-hour recovery time. In this equation, Y represents the increased effectiveness, expressed as an annual percentage relative to the 72-hour baseline. X denotes the treatment depth in inches. It's important to note that Y becomes 0 if X is greater than 4 inches, ensuring that we don't calculate any negative percentages for increased effectiveness. This adjustment for a 36-hour recovery time is applied to a range of practices, including retention basins, rain gardens, permeable pavements, exfiltration systems, and swales. The BMPFast software specifically applies this increased effectiveness for any recovery time between 3.1 and 36 hours. Within this particular range, no further adjustments are made because the differences in annual removal percentages between, say, a 72-hour and a 36-hour recovery are relatively small, and we currently lack sufficient simulations or field data to validate more granular increases. Field measurements of recovery time, particularly in highly percolating rock and soils like Florida's limestone, frequently show systems recovering in less than 3 hours. This slide discusses the increased effectiveness when recovery times are so short. Wanyelista's work involved completing cumulative frequency distributions for sites across all meteorological regions. When comparing these rapid recovery times to a standard 72-hour recovery period, an increase in removal effectiveness was noted, reaching up to about 9%. This figure is based on rain frequency distributions and simulations. An average is typically used for each rain zone due to small variations, with the accuracy of these simulations assumed to be around 1%. To mathematically incorporate this increased effectiveness, a best-fit polynomial curve is employed. This curve provides a relationship to be added to the removal calculations that assume a 72-hour recovery time. In this relationship, Y represents the increased annual effectiveness relative to 72 hours, expressed as a percentage, and X is the treatment depth in inches. It's important to note that this increased effectiveness approaches zero at a treatment depth of 4.0 inches, meaning if X is greater than 4 inches, Y becomes zero, and no negative percentage numbers are possible. This adjustment for increased effectiveness applies to any recovery time less than 3 hours, and is automatically incorporated into the BMPFast software for such scenarios. It's important to understand that while we're talking about very short recovery times, no further adjustments are made for recovery times specifically within the range of 1 to 3 hours due to the very small differences in annual removal percentages expected in that particular range. This methodology is applied to various best management practices, including retention basins, rain gardens, permeable pavements, exfiltration systems, and swales. Here, we're presented with an example problem designed to illustrate the input data and removal effectiveness of a retention basin using the BMPFast software. The project involves a planned retention basin for a 12.0-acre residential subdivision situated south of Orlando, Florida. The development site is characterized by hydrologic group soil A, and from the pre-application meeting, we know the average annual rainfall in this area is 52 inches. Regarding land use, the existing condition is defined as citrus, with a non-DCIA curve number of 50 and 0.0% directly connected impervious area. The post-development land use will transform into a single-family residential subdivision, with a non-DCIA curve number of 64 and 27% directly connected impervious area. The primary objective for this retention basin is to provide treatment sufficient to meet discharge requirements for an outstanding Florida water, or OFW, based on annual nutrient loads. The initial design considers a storage range, giving us two optional retention volumes to assess, 0.33 acre-feet and 2.5 acre-feet. This design must maintain the existing watershed characteristics, and the basin is specified to have a recovery time of 36 hours. Our key questions for this problem are: what size of retention basin can effectively be used to meet those OFW performance standards, and what can be done to protect the groundwater in this scenario? The retention treatment depth, or TD, for runoff storage is calculated as the volume divided by the area. For example, a 0.33 acre-feet volume over 12 acres results in a 0.33-inch treatment depth. To aid in your understanding of the annual assessment for total phosphorus and total nitrogen removal, please open the BMPFast software now. We will use this software to input the project data and evaluate these parameters. I encourage you to pause this presentation if needed while you open and familiarize yourself with BMPFast. This will greatly facilitate your use of the tool as we work through this example. Ultimately, the software will help us determine if a solution, perhaps with a treatment depth equivalent to 2.167 acre-feet, can effectively meet the required performance standards. We're now focusing on the navigation and data input processes within the BMPFast software. After you've successfully entered your site-specific and catchment data, the next step in the workflow is to input the treatment data. Following that, you will then configure the routing and specific best management practices, or BMPs, for each individual catchment. It's important to understand the flexibility and limitations here. You can enter data for multiple BMPs within a single catchment. For example, you could include both a retention basin and a rain garden within the same catchment. However, you cannot assign fundamentally different primary types of BMPs to one catchment without creating an additional catchment. So, if you wish to evaluate completely distinct BMP approaches for an area, you'll need to define additional catchments accordingly. To truly become proficient and efficient in utilizing the software for various assessments, I strongly encourage you to actively engage by entering all the data and continuing to navigate through the software yourself. Here, we're looking at how the watershed characteristic data were entered into the system. If you're following along with your own BMPFast software, it's a good idea to cross-reference your entries with what you see in this presentation to ensure consistency. Based on these entries, the software automatically calculates the annual runoff coefficient, the annual runoff volume, and the total nitrogen and total phosphorus loadings. These calculations are derived using the event mean concentrations, or EMCs, which are hardwired directly into the software. For this particular scenario, the proposed best management practice, or BMP, is retention. However, if a wet pond were the agreed-upon solution, and both the review agency and the plan preparer were in agreement, then the appropriate wet pond area could be entered into the system. It's also worth noting that there were no additional loadings from pumped or groundwater discharges to account for in this specific case. Here we see a schematic illustrating a typical cross-section of a retention basin, which is one type of best management practice. These basins are generally not very deep, typically ranging from about 3 to 7 feet for most locations. A critical design parameter for these basins is their ability to recover their full treatment volume within 72 hours. If a basin can be shown to recover more quickly, adjustments to its calculated removal effectiveness can be made. For instance, we can calculate effectiveness for recovery times as rapid as 3 hours, or for times falling between 36 and 72 hours. It's important to note that while there's a range, specific recovery times of 3 and 36 hours are primarily used to determine effectiveness due to available data. Overall, there are 13 different BMPs that are recognized for having designs that result in a measurable removal effectiveness. However, not all of them are encouraged in every area, often due to local code restrictions or the practicalities of long-term maintenance practices. The retention basin, as depicted here, is a widely used option and is permitted in areas of the state that can effectively support the required recovery time for treatment or infiltration. Finally, a practical detail for using the worksheet. Once a BMP's data is entered and its configuration is established as the selected BMP, that entry will be highlighted in green within the worksheet. For this particular design, we've selected the retention basin as our treatment option. We're initially setting the retention volume at the lowest practical value, which is 0.33 acre-feet, with a recovery time of 72 hours. With these parameters, we anticipate an annual removal efficiency of approximately 65% for both nitrogen and phosphorus. It's important to understand that this 65% represents an annual capture efficiency, assuming the average pollutant concentration throughout the year is equivalent to the event mean concentration. However, for outstanding Florida waters, or OFWs, the specific removal targets are more stringent, 80% for total nitrogen and 90% for total phosphorus. If we want to evaluate whether a larger basin could achieve better removal, we can assess this by examining the marginal change in annual removal as a function of the treatment depth. This can be visualized using the plot button available on the retention worksheet. Using the plot option provides valuable information regarding the optimal retention depth. This depth, often referred to as TD, can be adjusted to either increase or decrease the average annual effectiveness of your project. For this particular project, we're working with a maximum possible retention depth of 2.5 acre-feet, which translates to 2.5 inches. What's particularly useful here is that the graph of annual removal clearly illustrates that a removal effectiveness of 90% can be achieved with a retention depth of less than that 2.5 inch or 2.5 acre-foot maximum. This demonstrates how utilizing the plot options significantly enhances the value of the software's discovery capabilities. This slide focuses on determining the treatment depth required for a specific removal percentage, exemplified here by 90%. The getDepth function in the software is designed to calculate the necessary retention treatment volume and corresponding depth to achieve your desired removal effectiveness. After you specify a removal percentage, such as 90%, the software will prompt you, asking if the physical watershed conditions can accommodate the calculated retention volume, and seeking your acceptance. If you choose not to accept the proposed volume, you have the option to set a different volume yourself, and the software will then recalculate a new removal percentage based on your input. However, if you accept the calculated volume, both the treatment depth and volume are saved and will appear in your project printout. For our current example, achieving a 90% removal requires a retention volume of just 0.993 acre-feet, which translates to almost 1 inch of treatment depth. We'll proceed by accepting this retention volume. As we know, our site has ample capacity, up to 2.5 acre-feet, available. Now this brings us to an important consideration. Does achieving this 90% removal also fulfill the net improvement criteria often required for outstanding Florida water's discharge performance? The answer, which might surprise some, is no. This is a valuable learning point, and I strongly recommend that you run the BMPFast software yourself to observe and understand this specific result firsthand. Our focus here is on adding protection for groundwater supplies, which includes critical areas like springs and estuaries that have very focused impacts. The primary goal is to estimate both the recharge volume and the concentration of any substances reaching the groundwater. This is crucial when, for instance, a property owner wants to safeguard a groundwater source on their land and needs to understand the quantity and quality of water provided by a retention basin. Protection efforts are particularly common in spring areas, which often have dedicated programs to maintain water quality. To initiate this process within our system, you would select the groundwater analysis option on the Site Information worksheet. From there, it's essential to ensure that your retention basin design includes specific provisions engineered to protect the underlying groundwater. Sorption media plays a crucial role in safeguarding our groundwater. These materials are specifically chosen to effectively remove both total nitrogen and total phosphorus from infiltrated water before it enters the ground. For instance, a notable example is the Bold and Gold CTS24 media, which is a blend of clay, tire crumb, and sand. When you're making your selection, you'll have access to a drop-down menu that provides 6 different media choices, as well as the flexibility to define your own. Here, we're looking at the impact of treatment on groundwater discharge, specifically focusing on nitrogen concentration and recharge volume. Without any treatment, the nitrogen concentration discharged to groundwater from the pre-existing citrus land use was 2.11 milligrams per liter. For the post-land use condition, representing a single-family development without treatment, this concentration would be 1.77 milligrams per liter. Now, by implementing BAM treatment, utilizing a specialized Bold and Gold sorption media placed at the bottom of the retention basin, we see a significant improvement. The average total nitrogen concentration discharged to the groundwater is drastically reduced to 0.44 milligrams per liter. This demonstrates a substantial reduction compared to both the existing citrus condition and the untreated post-development scenario. The treatment depth in the retention basin, approximately 1 inch, manages an impressive average recharge volume of 3.77 million gallons per year. Both the reviewing agency and the property owner are satisfied with these results. However, the owner's maintenance plan for the site specifies that the media should last for at least 10 years, which means the design must account for providing sufficient media for that lifespan. To get started, please open the BMPFast software and navigate to the Treatment Options worksheet. Once there, you'll see a Tools Calculation button. Click on that, and then select both the Media Filter Minimum Surface Area and Service Life options to bring up those specific calculations. To treat up to 1 inch of runoff, the minimum calculated filter area required is 587.25 square feet. It's important to remember that this design needs to physically support the treatment process. To ensure proper function, half of the treatment volume must be processed within a single day. Furthermore, we apply a safety factor of 2 to reduce the treatment rate, providing an additional margin of safety. While the initial treatment rate at a 1-foot head was 10 inches per hour, applying this safety factor brings the adjusted rate down to 5 inches per hour, which also translates to 0.052 gallons per minute per square foot of media. Ultimately, the actual physical section and pond elevations must be carefully considered to accurately determine the area needed to ensure complete drainage within 72 hours. Here, we're looking at the critical interplay between the volume of a filter's media and its projected service life. In this particular scenario, the design mandates that the system's recovery time must be less than 72 hours. To meet this requirement and achieve optimal performance, an agreement was reached between the reviewer and the applicant to utilize 5,400 cubic feet of media. Installed to a depth of 2 feet, this specific media volume directly influences the filter's service life, which, in this case, is calculated to be 10.5 years. A fundamental principle in filter design is that a greater volume, or weight of media, generally corresponds to a longer service life because it provides more capacity for pollutant removal. When selecting a media for nutrient removal, you must consider its inherent capacity to remove orthophosphate, or OP. This involves understanding the media's removal rate, typically expressed in milligrams of OP per gram of saturated media, along with its saturated weight. The ultimate service life is then determined by this OP removal capacity, factoring in the media volume and the annual treatment rate for OP. For a deeper dive into these specifics, particularly concerning biosorption activated media, or BAM, please refer to our dedicated learning modules on the topic. The outcome here demonstrates that with careful planning and selection, a robust and long-lasting solution is entirely achievable. Throughout this module, we've gained a comprehensive understanding of retention BMPs. We learned exactly what a retention best management practice is, recognizing it as one of the foundational approaches for water quality control. A key function of these BMPs is their ability to retain a portion of the annual runoff, preventing its discharge, often through infiltration, a process valuable for both flood control and groundwater recharge. We also navigated the process for conducting an annual mass removal analysis using a retention basin BMP, which is crucial for evaluating its effectiveness in pollutant reduction. This led us to explore discovery methods using retention plot options, enabling us to identify optimal designs for basin depth and volume. A significant focus was placed on groundwater protection, particularly when retention relies on infiltration. We learned how using specific media can protect groundwater by removing pollutants like total nitrogen and total phosphorus. Additionally, we understood the insights we can derive from the Service Life Worksheet, which helps us determine the operational lifespan of such protective media. Finally, we broadened our perspective to recognize that the effectiveness of many other BMPs, including exfiltration systems, permeable pavements, swales, and rain gardens, is intrinsically linked to and dependent upon these same fundamental retention curves and principles we've thoroughly examined. This concludes our information on understanding retention, which included a look at navigating the BMPFast software. You are encouraged to view other learning modules if you need additional support, and consider applying to take the competency test. For more specific details on that, please refer to the learning module titled Self-Test. Thank you for viewing and listening to this presentation.